Back to YouTube channel Chemistry Live UGPG. So today we are going to talk about valence bond theory part 2. So this will be highly beneficial for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So this is the syllabus, Core 1 paper, Unit 4, Chemical Bonding. So we are going to talk about valence bond theory, Hitler-London approach, part 2. So as we discussed in part 1, so there are various structures between which the resonance occurs are called contributing or resonance structures. So let's talk about what is resonance. So resonance is the description of the electronic structures of a molecule or an ion by means of several schemes of a pairing of electrons with the features of each scheme contributing in the description. So as a result of resonance, the energy of molecule is lowered and it acquires a minimum value. So this lowering in energy is called resonance energy. That is equal to difference between observed and calculated heat of formation. So it is the greatest when all the resonating structures are of same energy. So for example, this carbon monoxide. Here the calculated value for this one 1.22 angstrom and experimental is 1.13 angstrom. For this one it is 1.10 angstrom. So the calculated heats of formation for carbon monoxide is 175 kilocalorie per mole and the observed heat of formation is 256 kilocalorie per mole. So resonance energy will be 81 kilocalorie per mole. So here are some resonating structures for carbon dioxide. So you can see here how the double bond will resonate and resonance energy is found to be 33 kilocalorie per mole. Similarly for carbonate. So these are resonating structures and for O2 molecule. So these are the resonating structures. So in O2, although all these structures can explain the bond energy and bond distance in O2 molecule, but it failed to explain the paramagnetic property of oxygen molecule. So in order to account for paramagnetism, so this structure is proposed, where you can have two unpaired electrons. So thus O2 molecule has one 2 electron and two 3 electron bond, and each of 3 electron bonds has one unpaired electron. So this explains the presence of two unpaired electrons in O2 molecule. The next is conditions of resonance. So the relative position of all the atoms in each of the resonance forms must be same and the arrangement of electron may differ. And the number of unpaired and paired electron in each of the resonance forms must be same so that a continuous change from one bond to another may occur. Similarly, like charges should not reside on the atoms close together in a contributing form, but unlike charges should not be greatly separated, and the contributing structures should be of almost equal energy. Then next is the features of valence bond theory. A covalent bond is formed due to overlap of atomic orbitals, each of which contain one electron of opposite spin. Each of bonded atom maintains its own atomic orbitals, but the electron pair in the overlapping orbitals is shared by both the atoms. The next is the greater the amount of orbital overlap, the stronger the bond. The electrons which are already paired in the valence shell cannot participate in bond formation. So those are called lone pair of electrons. So they cannot do so if they can be unpaired without using much energy. So for example nitrogen. So valence shell electronic configuration is 2s2, 2px1, 2py1, 2pz1. These valence unpaired electrons can form bond with fluorine atom, and fluorine has one unpaired electron, so you can easily get NF5, but you cannot get you can get NF3 but not NF5. Similarly phosphorus, the valence shell configuration is 3s2, 3px1, 3py1, 3pz1 and 3d0. It can form PF5. So this one of the 3s electron can in excited state go to the 3d orbital. So here you can have 5 unpaired electron, and these 5 unpaired electron form bond with 5 fluorine atoms, giving rise to phosphorus pentafluoride. Then next is orbital overlap or mixing, or you can call it as sp mixing, that lead to sigma or pi bond. Similarly, covalent bond is formed due to overlap of atomic orbitals, we know, and covalent bond is also two types, sigma bond and pi bond. And a covalent bond, sigma bond, is due to overlap of orbitals along their axis. So that is end to end or head on overlapping. And head on overlapping means there will be maximum overlapping, and that lead to sigma bond, and which is a strong bond and it has axial symmetry. So if z axis is the molecular axis, so sigma bond is formed by SS or SPZ or PZ overlap. So sigma bonds are called SS sigma, SP sigma or PZ sigma bonds respectively. So here you can see hydrogen atom. So 1s orbital, 1 electron, so atomic orbital. So here again another hydrogen atom, so they overlap, giving rise to 1s sigma bond in hydrogen molecule. Similarly, here in X atom you have 2pz1 and 2pz1, so they can overlap, giving rise to pz sigma bond, axial overlapping or head on overlapping. Similarly, s orbital along z axis, so and here pz orbital. So the radius of s orbital is 1 unit and the radius of p orbital is √3 unit. So the bond length is taken equal to the product of magnitude of the bond orbitals of the two atoms forming the bond. So the strength of bond of SS bond equal to 1 into 1, so 1, SP bond, that is 1.732, and PP bond is 3. So hence p orbital can overlap with s and p orbital more effectively than two s orbitals. Similarly, pi bond. So pi bond is also a covalent bond, is formed by overlap of orbitals in a line perpendicular to the molecular axis. So that is due to side by side overlapping or lateral overlapping. So if z is the molecular axis, so px overlap or py orbital overlap gives pi bond. So in case of oxygen atom, this is the valence shell configuration, 2s2, 2px1 and 2py1 and 2pz1. So here 2py1 and 2px1. So those can undergo lateral overlapping, giving rise to a sigma bond. Sorry, pi bond. Similarly, in case of nitrogen, so we know that is a n triple bond n. So valence shell configuration is 2s2, 2px1, 2py1, 2pz1. So this 2pz overlap will give sigma bond, and 2px and 2py overlap giving rise to pi bond. So a sigma bond determines the direction of the bond and the extent of internuclear distance, and pi bond shortens the internuclear distance. Similarly, in case of HX molecule, so s orbital of hydrogen atom and p orbital of X atom overlap, giving rise to SPX bond, HX molecule. Similarly, you can find the similar case in case of water and in case of ammonia. So here you can get two sigma bonds. So oxygen overlap with two hydrogen 1s orbital, giving rise to HOH, so two sigma bonds, and NH3 case also you get three sigma bonds. So next is limitations of valence bond theory. So valence bond theory explains the covalent bond is a result of sharing of electron from both the atoms. Hence it cannot explain coordinate bond, in which one of the bonded atom furnishes both the electron. So according to valence bond theory, O2 molecule is diamagnetic, but experimentally O2 oxygen molecule is paramagnetic. So that is presence of unpaired electrons in it. Valence bond theory considers the formation of odd electron molecule or ions such as H2+, where no pairing of electrons occur. So please subscribe to our channel Chemistry Live UGPG. This is also available in the website www.chemistryliveugpg.com. For class 11th and 12th, this is the channel Foundation Chemistry AV. So this is a simple step towards e-learning making life better. Thank you all for learning.